Thank you for the opportunity to present today. My name is Luke Pinkerton. I'm the president of Helix Steel. For those of you who haven't heard, we were very recently acquired by the Forta Corporation, so I also have some new roles with Forta as well. So I'm going to talk mainly today, and I'm glad nobody else did this. I just went to the CT23 guide and just looked up the definition for durability. And what I wanted to do is go through some live actual use cases where customers came to us because they needed one of these things. They needed the ability to resist weathering, action, chemical attack, abrasion, or other conditions of service. Obviously, this plays into LCA as well. The only other mention of durability in the CT is the durability factor. So to your point earlier, maybe we need new standards, new tests to assess durability. So these are the things I'm going to cover. I'm going to have to go quick because I'm going to cover a bunch of use cases. So we'll go through it and then we can come back with questions. I'm going to start with an introduction to the twisted steel micro reinforcement technology. I'll show you a picture of it in a moment, but we make a product that is twisted. I think in Nicholas's presentation, there was actually in the fiber types, there was a twisted reinforcement there. So it works very much on the same principle of a screw versus a nail. So what we're trying to do is put small discontinuous reinforcement in the concrete that's stiffer than the concrete and bonds to the concrete better than something with discrete anchorages, for example. So when we talk about durability, often what we're trying to do is prevent that concrete from eroding or breaking down. So sometimes in structural engineering, we call that serviceability. In order for a structure to be serviceable, that can mean different things. Obviously, deflection is one thing that comes to mind, but cracking is another. So what we really want to try to do if we're talking about making a structure durable or resistant to things like weathering is we want to stop it from failing in the first place. Keeping it together after it fails is helpful, but if we can put something into the concrete or we can design that mix to make it so it doesn't crack or is more resistant to cracking in the first place, it's even better. So that's kind of where the twisted steel micro reinforcement or Helix product comes into play. We have something that is 10 times stiffer than the concrete and has continuous bond. Load follows the stiffest path. If you put enough Helix in there, you're able to form a matrix of reinforcement that can carry load and encourage this micro cracking as opposed to really only providing something that provides strength after the concrete cracks, like rebar. So we also, in kind of our tradition of doing things a little bit differently, define durability mathematically, and I kind of just took a very simple approach. We like to do direct tension testing, and what we do a lot of times is we'll say durability is related to the area or the energy it takes to form a 1 millimeter crack. Now that's completely arbitrary, but it serves as a comparison. So a lot of times we will compare just what the plain concrete can do, which is really just that point up to that sigma C, versus what something that has the reinforcement in it can do in terms of energy absorption. We have two products. One is a 1-inch product. We call it 525. It is galvanized, and we'll talk about that in the use cases. And then we have an 852 product that's responded a little bit more to the industry, which seems to have gone to more of a 2-inch, larger diameter fiber spec in a lot of areas. We like the smaller diameter product. We like the galvanizing because you get more pieces per pound, which helps form that network. I'm not going to get into design today because we're focusing on durability, but there was a paper that was published, or an article in Concrete International last fall that Mahmoud and I were co-authors on that was talking about how you can get building code compliance with alternative materials. So if you're interested in that, you can scan that and it'll give you the paper. So at this point, we're going to go into the use cases. And in each of these use cases, I'm going to warn you a little bit. They're a little bit anecdotal, okay? These are customers that have come to us and asked us for something. But there is some data to back. So I'm going to start with some data and some testing, and then I'm going to talk about the application. So the first one is weathering. What tests do we have for weathering out there? You can look at some of the 544 documents. This is an older one that's talking about abrasion, cavitation resistance, erosion resistance. You can also look at like the ASTM C672 test. I'll talk about the C666 test. The 672 test is more aggressive. It's not designed for fibers, but it's more aggressive because it's salt spray. It's spraying rather than immersing, which is it's more corrosive. So we had a customer who was actually the U.S. who was dealing with jetties that are all up and down the west coast of the United States. Extreme conditions that you have to cast in. You know, you've got salt water, salt spray. These jetties that were built in the 50s were breaking down and falling apart, basically. So the Corps came to us and said, we need a galvanized, we want steel, we need it to be galvanized, we want the corrosion resistance, and we need to be able, we can't put rebar out on this jetty. It's just not practical. So we went out and we provided, this was a 75 pound per cubic yard dosage of our 525 product on this jetty, no reinforcement at all. It's a broom finish. A lot of people ask, well, can you finish it? You know, with a broom finish, you can. There's just certain best practices that you need to follow. And the other thing that was interesting about this is they actually had to avoid the high tides to pour because the water would come up. So they had to do it very quickly. Doing that with rebar is very difficult. So definitely a beautiful sight at the end to see the jetty completed. So that's an example of obviously chemical attack as well as weathering from water. So I'll give you a little summary at the end of all of these and kind of how they all stack up in terms of that durability number that I mentioned before, but we'll go into another one here. Again, going into chemical attack, but this time also adding freeze-thaw to the question. We do have some tests that can be used for fiber reinforced concrete for freeze-thaw. There's the ASTM C666 test, which I believe is specified maybe in some, it may be one of the, or at least mentioned in some of the 544 documents. It gives you a durability factor, and you know, a lot of it has to do with the mix itself. The fibers can help, but you got to have air entrainment in there to pass this test. So typically an 80 or better durability factor is considered passing. You can see that we've tested some different dosages of the product, and we do get an increase as we do that. So how does that translate into real life? So Utah Department of Transportation, in conjunction with BYU University, cast 4 bridge decks. And you can see there's a lot of rebar there. They didn't take the rebar out in these decks. They added the reinforcement in on top. When they did that, what they got was, and you're not going to be able to see it very good here, this was taken 5 years after. You'll see on this side is conventional. You can't see some of the hairline cracking, but they did something really neat. They did this crack mapping. So they actually, I don't know if they had the graduate students go out there and crawl around on the deck, or if they had, you know, I don't know how they did it, but it was scientifically done. You have quite a bit of crack density on that conventional design, and what they concluded was, and this was Spencer Guthrie at BYU University and his students, there was a whole PhD thesis written on it, you can scan that and get it, is that there was a significant reduction in crack density with the use of the product at 40 pounds per cubic yard. And you know, they actually recommended the product be used to reduce the occurrence of larger cracks in bridge decks as a result of this. So bridge decks are something that are very expensive to replace, to deal with, and you know, provide an opportunity. You know, there's a lot of states that are in really bad shape, like Missouri, for example. They've got a lot of bridges that are deficient, and it's just if we can increase the life by maybe spending a little bit more at the beginning, it goes to the life cycle discussion. All right, one other example, and we were talking about extreme applications. This is actually a low water crossing up. Anybody watched that ice road truck show a few years back on the Discovery Channel? This is right at the end of the ice road. This is a low water crossing, so that goes underwater every year. And again, they had to go in there, pour this road, and get out before that water came up. And there's heavy trucks that are servicing oil fields up in Dead Horse, Alaska. And again, similar application, 45 pounds. This one does not have rebar in it. All right, abrasion. Abrasions, I'm gonna argue that maybe fibers, maybe somebody in here would disagree with me, but fibers can maybe help with abrasion, but you really have to, it really is a mixed design issue as well. So there's a Chaplin abrasion test that you can run that actually scores a circular pattern, and you go by the depth. If you have a good mixed design that has good packing density along with a fiber in it, or maybe a surface hardener or densifier, you can get really good abrasion. And that's really important in warehousing type environments. A lot of these places, they want to push these pallets. If you go into these data center, or not data centers, the warehouses, they want to slide pallets around, and you really want to have a good abrasion resistant floor to do that. Moving on in our marathon here, impact and fatigue. So there is quite a bit of discussion in here on impact and fatigue in ACI documents. 360 has a whole table in it that talks about really the factor of safety. You higher the factor of safety on cracking or modulus of rupture, the more fatigue resistance you have. There's also this concept of fracture toughness that if you get into fracture mechanics, you can study, but that's mainly it's dependent on sort of the material size and that modulus of rupture. This is a case where fatigue resistance was really important. It was a recycling center. So at these recycling centers, they have wheel loaders that are loading up scrap, basically. Over Christmas, I was doing some spring cleaning, and you basically take all your stuff, you dump it, and then they come and scoop it up. What you're seeing here is a slab that they poured the year before. They poured with the twisted steel micro reinforcement product in it. And it's going to transition over past this spalled area to an area that had the Helix product in it. This was taken 4 years after the project was poured. And if you look closely there, you'll see a lot of abrasion, but you won't see the cracking that occurred in the other slab. Repetitive vehicle loading is another one that is maybe considered under that other category there. There are ways to assess that. This was a test that was run by the Mexican Highway Authority where they ran 5 million easels on Helix reinforced pavement. And what we were trying to do here is decrease the thickness while not reducing the strength. And there's a whole report on it. If anybody's interested, I'm happy to get it to you. But we did find that we were able to do that with this study after the 5 million easels. This is some pictures of some highway placements in Mexico and more residential. And then last is the hurricane and tornado resistance. So that is the FEMA test for tornado resistance. You could argue that concrete on its own probably is going to stop that 2x4, but we have implemented the product in the Villages in Florida, which has been hit by 8 tornadoes and 5 hurricanes since we first started working in that development. They just do single-story cast-in-place walls there, but with weather conditions getting worse in certain parts of the world, having concrete structures really kind of makes sense, and they do look good. So wrapping up, these were all applications we looked at. We flew through 7 applications. These applications date back to 2007, and sort of, were intended to illustrate kind of those opportunities where we were able to provide more durability to the customer. That Helix durability is the comparison with plain concrete in that little simple energy model that I showed, and then the study is some of the tests that we talked about. So that's it. Does anybody have any questions?